random variable or normal random variable or Gaussian random variable, right? So we will study this Gaussian random variable, right, more closely, right? And then we'll use some of its property, right, to analyze, right, the fading margin that we need for the shadowing. Okay. So let's see. So we have this random variable x, right? And again, this is can be distributed, right? Or it's normal, right? Or Gaussian random variable. When I say Gaussian, there's two parameters that capture Gaussian random variable. There's a mean, right? So in this case, the mean is equal to 0. There's a variance. Variance is the variation from the mean, right? In this case, I set it to be 1, right? So variance is basically the standard deviation raised to power of 2. Okay, so bigger variance means there's a bigger chance that the sample will be away from the mean. Okay, so this is what we call standard Gaussian. That means Gaussian with mean 0 and variance 1, right? Unit variance, right? Okay, so what does that mean, right? So if I run some experiment, right? If I try different values of x, so here's 0, right? So that's the mean. And you see that if I run or if I try to output the values of x, you get something here, you get something here, right? Or sometimes you get something that is less than 0. So Gaussian could be bigger than 0 and less than 0. There's a lesser chance that the x will be very far away from 0, right? And in both directions, right? So this red mark, right? This is samples, right? So I sort of run many samples and see what's going on. Okay. What you can do is you can do an histogram. What is an histogram, right? You sort of divide the x value into smaller bins. For example, if x fall into this sort of value, then you count the number of samples, right? So the axis here is the random variable, right, or the output, right? And I divide into smaller bins, right? Many bins, right? And for example, if you run this random variable and it's the value is in this bin, then you count the number of samples, right? And you do this many times, right? And you see that there are a lot of samples that is close to 0, right? So you see the bigger graph. So the y-axis is the number of samples, right? And as x getting away from the mean, right, or 0, you see that the graph is decreasing, or the number of samples will be smaller and smaller, especially when x is very large, right? And this happened on the left hand side too. Okay. Now, if you run this experiment, right? If you run the number of samples very large, that is, it's going to infinity, and the bin is very fine, right? Very fine bins and many bins, right? And again, you take the number of sample in each bin. This, sort of, rectangle, pixelate, histogram, right? It's gonna become smoother, right? Something like this, right? Okay. So this is gonna be, some function that tell us, right? If x value is close to 0, there's a bigger chance, right? Because there are a lot of sample here that's gonna happen. Okay. So this graph, right, or this function, right? This is what we call probability density function, right? Probability density function, or PDF, of this random variable x. What does it tell us? It tells us that, okay, so any value that is close to 0, close to the mean, there's a bigger chance that you see that value because the density, the probability density is very high. But if x is far away, right? For example, x is 100 or 1000, there's a lesser chance that you will see it because the function is the probability density is very low. Okay, you got this? So this is what Gaussian PDF looks like. Okay, it's like a bell, right? Okay. Okay. This function has, this nice looking equations, right? You can describe the function in terms of, variable x, right? So, right, Gaussian random variable could be negative number, could be positive number, could be anything, right? So x could be from minus infinity to infinity. And the density function, right, it's captured by this expression, right? 1 over 2 pi e to the power of minus x squared over 2. Okay? Now, what does this density do to us, right? So hopefully this is a review, right? You can find the probability, right? So the graph is probability density. You can find the probability from this graph by looking at the area under the curve. For example, I want to find the probability that the random variable x will output the value that is, smaller than a, right? Less than or equal to the value a, right? Okay, I'm looking for the probability that the random variable or the percentage of time that the random variable x will output some number that is less than a. How do I find this? Right. So if we know the PDF, then you could do this, right? So for example, if a is some positive number, right? So a is over here, right? So 0 right here. So remember the horizontal axis is the x value. You're looking for when x is less than a. Where is x less than a? Well, a is right here, less than a. That means it's on the left of a, right? So anything that is what I'm masking here, right? Okay. So we want to find the probability. That means you want to find the area, right? Or the summation of this density, right? Right. From minus infinity to a. Okay. That's going to give me the probability of that event, right? So probability of, random variable x is less than or equal to a is area under the curve PDF when x is less than a. Okay. Now, this is from basic calculus, right? Hopefully, you remember this, right? Area under any functions you can use integral, right? So it's integrate, right? This PDF, right? Which we can, we know what the expressions is, right? It's a function of x. So we integrate with respect to x. We start the integration from minus infinity to a, right? Remember, right? We go from very far away to the a, okay? Okay, everyone got this? So you can do the integrations, right? Maybe you cannot do the integration. That's why you can, put it in some program, right? And then you can specify what the a is. Then it's gonna do the integration for you. So at the end, you get a number, right? So that number will tell us the probability of that event. Okay, everyone got this? So we know what the PDF of Gaussian is. We know how to find the probability of event. Okay. Now let me give you an example. What if I want to find the probability that x is less than infinity, and I'm sorry, x is bigger than minus infinity and less than infinity? Okay, so basically that means it's the whole axis, right? This event cover the whole x value, right? Every possible x value. That means we want to find the area under the curve of this whole graph, right? So again, area under the curve, right? So we know what the PDF is, right? We're gonna integrate from minus infinity to infinity. What do we get? If we integrate PDF, what is the total probability? What is the biggest probability it could be? It's equal to 1, right? That means it's always the case, right? Right? This is always true, right? X will output something that is between minus infinity and infinity. There's no questions about this, right? You don't need to actually do any calculations. You can answer. It's gonna be certain, right? That means probability is equal to 1. Okay. What about this? Let me ask you this. What if I want to find the probability that x is bigger than 0? How do you find this? Pongsathorn, what do we do?
So we take the all area which is 1 divided minus by the area of x lesser than a.
Okay, so x bigger than 0, where's the 0? Right here, right?
The middle.
Yeah, so bigger than 0, which way? Is it on the right or on the left of 0?
On the right.
Right, so bigger than 0, that means right here, right? Everything here.
Yes.
So that means we want to find area under the curve, right? On this.
0.5.
Right, right. So very good, right? So you know right away, right? Because the graph is symmetrical. Everything sum up to 1. So that means if we only take a half, right, of the graph, then it's equal to 0.5. That means this probability, right? If you want to be, complicated, then you write, this whole integral, right? But actually it's equal to 0.5. Yeah. What about this? Next one. Can someone help me with this? How do you find that probability? Apithan. Yes. What do you do?
Area under the graph between -1 and 1.
Very good. Right. So you look at the event that they are looking for, right? They're looking for x between -1 and 1, right? Again, you look at this, PDF, and you look at the horizontal axis. So we want x between -1 and 1. So that means this segment of the graph. So that means we want to find this area. What is this equal to, Apithan? What is this equal to?
1.
Really? No, not 1, right? 1 have to be area of the whole thing. Cannot be 1. Has to be less than 1, right? Right? Has to be between 0 and 1, but we don't know what it is, right? But if you want to know, you can do the integration, right? So you can set this integration up, right? And you know that the PDF is 1 over square root of 2 pi, right? E to the power minus x squared over 2, right? You can do this using MATLAB or some program, right, to compute this. So it can give you number, but we don't know what this is as of now. Right? The integral from z, right? So what is z? Remember, z is the input from z to infinity of the Gaussian PDF. Okay, you integrate with respect to x, right? So remember, the Gaussian PDF looks like this. You integrate with respect to x, right? So once you integrate, you plug in z, you plug in infinity, and you're gonna get some number, and that's gonna be the Q functions. Okay. Everyone got this? Yeah? Yes, no? Maybe? Okay, so in terms of area under the curve, for example, it's z it's here, right? Let's look at what we have here. We integrate from z to infinity. Z to infinity means, right here, right? To infinity. So that means it's the tail. It's the right tail, right? So we want to find the area of this right tail. and that's gonna give us the Q function, right? So this is area under the PDF of standard Gaussian, right? From x equal to z to x equal to infinity, and this is equal to the Q of z. Okay, so let's try some example. What is the Q function of minus infinity? Jane Gila, turn on your microphone, please.
Yes,
Yeah. So what
I
is Q
think
function of minus infinity?
I think it's 1.
How do you know it's 1?
I guess it's a integral of minus infinity to infinity.
Okay, very good. And then integrate of the whole PDF is equal to 1, right?
Yeah.
Or okay, so you think of this as z, right? Z is equal to minus infinity. Where's minus infinity? It's way out here, right? This is minus infinity. And remember, right, Q function take on the right tail, right? So everything toward, right, on the right, right? So that means starting from that z value and then everything until until infinity. And you see that it, it's everything of the PDF. So this is equal to 1. Second one, what is Q of infinity? Genjila.
Maybe 0.
Not maybe, it's equal to 0,
Okay.
right? Again, why is it 0? Remember, this is the z, right? Z equal to infinity. Where's infinity? It's way out here, right? Look at my marker there, right? So there's nothing here, right? To the right, so that means nothing, right? Nothing out here, nothing out here. So there's no area under the curve. There's no area, right? So that's why it's equal to 0. Okay. What is Q of 0? Patpong. Patpong. Turn on your microphone, please. Can you hear me, Tatpong? Okay. So let me give you a hint. So 0 is the z, right? Where's the z, right? Right here, right? 0. Right? So Q function is what? Toward the right, right? Of z, right? So that means right here. What is that area? The one that I just shaded. No. Half, only half, right? Area, the whole area is equal to 1. If you only take half of 1 is equal to what? Zero 0.5, right? 0.5. Okay. Okay. What about if z is negative? Q of minus z, right? So we used to think of z as positive number. If it's negative number, right? For example, it's right here, right? It's on the left of 0. So that means the area that we are talking about, right? It's right here. That's going to be the values of the Q functions. How do we find this, right? Well, you can find this another way, right? You can think of, okay, what if I take the whole area, right? The whole graph, and then I subtract this, this part, right? You see, right? So I take the whole area and subtract this, this n, right? Right. So remember, right? The graph is symmetrical, right? So if negative z is right here, z is right here. So this area can be equal to this, right? It's equal, right? So you can take the whole area, which is equal to 1, right, minus with Q of Z. Right, so Q of minus Z is equal to 1 minus Q of Z. Right, okay. So if you got Q of negative number, right, you can use Q of positive power to find that, Q of positive input to find that, right? Well, I mentioned this property because we're going to use a table, and the table of Q functions only give positive Z, right? Okay. So we can find other values of Q function, right, with Q function table. So let's look up what the table looks like, right? So this is very convenient, right? So you don't have to do the integrations, right? So you see here's the Z value, right? Start from Z equal to 0, the output is equal to 0.5 as we see. As Q function increases, right, the tail will get smaller and smaller, and you see that the value, the output of the Q function is getting smaller. Okay. The third row, this is also Z, right? So from 1.9, now it's continuing with 2 until 3.9, right? And you see that the tail is going to be very small, right? Q of Z is equal to 0.00005, right? And you see that they only give you positive Z, right? What about if you are given, right, Q of some negative number? Then you can use this expressions to find out. Okay. Everyone got this? Sort of. Hopefully this is some sort of a review for you, right? It's not totally new for you. Okay, let's do some example. What's this? What is the probability of, this standard Gaussian is bigger than 0.5? Okay, again, right? If you draw the PDF, right? Here's 0, right? 0.5 is right here, right? Bigger than 0.5, right here, right? So that means we want to find this tail, right? And this corresponding to Q of 0.5, right? Okay, so Q of 0.5, you look it up in the table, right? So you see it's already in the table, right? Z is equal to 0.5. The Q value is equal to 0.30854. So the probability that the Gaussian random variable will be bigger than 0.5, it's 30%, right? 30.854%. Okay. Everyone got this? Sort of, yeah. Let's do this problem. Let's see what you got. Using this Q functions, Q table, function of this Q table. Table of a Q function, I'm sorry. Okay, so
Yes, yeah, got it. So just took I just took the value of 1, so C1, which is
Yeah.
0.15866.
Mm-hmm.
I multiplied it by 2 to get the value we couldn't get.
Mm-hmm.
And then I did minus 1 minus the value I just got.
Mm-hmm.
So 1 minus 0.15866 times 2.
Okay.
Which
And
is,
how did you come up with that?
So Q of 1 is the probability of the value which is above 1.
Mm-hmm.
V equals 1. And the curve is mirror. So it's the same probability on the right and on the left. So to remove the probability it's above 1 or under -1, it's the same one. I don't know how to explain it, but
I think you already did, sort of, right?
Yeah.
So maybe let me add to what Marlo just said, right? So I'm gonna use this again PDF of this standard Gaussian, right? You know, I apologize for my drawing, right? Sometimes it's you know fat, sometimes it's thin, but you know what it is, right? So this is symmetrical, right? And again, probability of this event, right? X is, you know, between -1 and 1, right? So that means we are looking for the area of this, you know, of this shaded area, right? Now, how do you find that, right? So what I think Marlo did, right? So he didn't find that directly, right? What he did is he find this purple shaded area, right? Because now this is, you can write this as a Q functions, right? Q function of what? Q function of 1. Right? The Z is equal to 1, right? Then you get that, you know, that purple segment, right? This is Q function of 1. Okay. So if you know this, you know, purple segment, it's the same as this, right? Because the graph is symmetrical, right? So what that tail on the right, it's going to be the tail on the left as well. And you know that the whole graph is, the area is equal to 1, right? So you subtract that, you're going to get this, you know, red area, right? Okay. That's how I would explain this, right? So this is equal to 1 minus Q of 1 minus Q of 1, right? So Q of 1 twice, basically. Okay. So Q of 1, right? So Z is equal to 1. You see that it's already given, right? It's equal to 0.15866. So you can find the answer, right? So it's 1 minus 2 multiplied with 0.15866. And you get what the answer, the final answer is 0.68 approximately, or 68%, right? Okay. So that's a big chance, right? If you run this, you know, random variable, it's gonna give you a number between -1 and 1 with the chance of approximately 68%, right? Okay. Everyone got this? Yeah. Okay. So you don't need to do integrations, right? You can use this, you know, table of these Q functions. Okay. Okay. Now, what if your, you know, your random variable is not standard Gaussian? Right? So it's still Gaussian, but it's not standard. What does that mean? Right? It's Gaussian, but not standard. So that's what this y is, right? So y is Gaussian random variable, but the mean is not 0. The mean is equal to mu, right? So mu is a constant, could be, you know, negative, could be positive, but it's not equal to 0. The variance is not 1. It's some other numbers, right? So this is positive, right? Sigma square. Okay. Well, you can always convert this into standard Gaussian, right? Which is mean 0, variance 1, right? How do you do that? You take the random variable, you subtract its means, right? So y minus mu. Now the mean gonna be 0. And then you divide it by its standard deviations, right? Right. So you take the random variable, you subtract its means. So the mean now is equal to 0 divided by standard deviation. Now what the output, it's going to become, you know, standard Gaussians, right? Mean 0, variance 1. Okay. We can use this, right? Now we can use, you know, the table of the Q functions, right? Because that's only referred to associated with, you know, standard Gaussian. Okay. For example, what if we want to find the probability that this, you know, some Gaussian, right? Gaussian random variable is bigger than A, right? Again, Y is, you know, non-standard Gaussians, right? So how do we do this, right? We want to go back to the same table, right? Use the same table. Okay. So we'll start with this. right? Now, what I did is this. I cannot subtract, right, the mean, right, on both sides, right? Whatever I subtract on the right, subtract the same thing on the left, right? So the bigger than sign is still there, right? There's no effect. I can divide both sides by positive number, right? So standard deviation is always positive. Okay. So now you look at this, right? This is standard Gaussian now, right? And it has to be bigger than this number. So remember what A is a number, right? Mu is a mean, right? It's a number too, and sigma is standard deviation. Standard deviation it's some number too, right? So that means you want probability of standard Gaussian that is bigger than this number, right? So again, the right tail. So that's come down to the Q function, right? So this is the set, right? Right. And you can use the same table, right, to find the answers here. Okay. Okay, so let's do another example. I want you to find, let's say y is some non-standard Gaussians, right? The mean is equal to -5, variance is equal to 2. Oh, make things a little bit easier. I'm sorry. So let's change this. Let's say this is the variance is equal to 4. So this is the mu. This is sigma square. Okay. So I want you to find probability that y is going to be bigger than 0. Find the probability of y is less than 0. Let's see what you get. Okay. So this is going to be the last example. Okay. Again, I'm going to give you 5 minutes. Actually, yet 5 minutes. Okay. So let's say we want to find the probability of y bigger than 0, right? Now, y is not standard Gaussian, right? So we want to make it into a standard Gaussian first, and then we can use Q functions, right? So how do we do that? We're gonna subtract both sides by the means, right? So what is the mean of y, right? So y, right? The problem tells us that the mean is equal to -5. The variance is equal to 4. Okay. So I'm gonna -5, right? On both sides, right? Okay. And I'm gonna divide both sides by standard deviation, which is 2, right? Okay, everyone got this? So now this is standard Gaussian, right? Standard Gauss, right? On the X, right? We want, in terms of standard Gaussians, right? We want it to be bigger than 2.5, right? So again, if I draw this, standard Gaussian PDF, this is 0, this is 2.5. That means I want bigger than 2.5. That means this. And that's corresponding to the Q function of 2.5, right? Okay. So this is equal to Q function of 2.5. Now you look it up in the table, right? You go back. 2.5 is right here, right? Q function of 2.5 is 0.0621. Okay. Okay, so that's the answer, right? Right. So the probability of this event is equal to this, is equal to this, is equal to this, which is this. Okay, everyone got this? So the chance is very small, right? So y mostly is negative, right? The chance that it's gonna be bigger than 0 is only 0.621%, right? Not even 1%. Now the other questions, right? The related question, the probability that y is negative, right? Well, it's on the flip side. That means it's 1 minus, right? 0.00621, which is 0.99379, right? Or 99.379%. Right? So that's the answer. Okay, anyone has any questions here? Right, so you can use this table of a Q functions, right, to find the probability, right, of any Gaussian random variable, right, in theory, right?